In mathematics, there are several ways of defining the real number system as an ordered field. The synthetic approach gives a list of axioms for the real numbers as a complete ordered field. Under the usual axioms of set theory, one can show that these axioms are categorical, in the sense that there is a model for the axioms, and any two such models are isomorphic. Any one of these models must be explicitly constructed, and most of these models are built using the basic properties of the rational number system as an ordered field. Synthetic approach. The synthetic approach axiomatically defines the real number system as a complete ordered field. Precisely, this means the following. A model for the real number system consists of a set R, two distinct elements 0 and 1 of R, two binary operations plus and times on R, and a binary relation on R, satisfying the following properties. Forms a field. In other words, for all x, y, and z in R, x plus equals plus z and x times z. For all x and y in R, x plus y equals y plus x and x times y equals y times x. For all x, y, and z in R, x times equals plus. For all x in R, x plus 0 equals x. 0 is not equal to 1, and for all x in R, x times 1 equals x. For every x in R, there exists an element minus x in R, such that x plus equals 0. For every x0 in R, there exists an element x minus 1 in R, such that x times x minus 1 equals 1. Forms a totally ordered set. In other words, for all x in R, xx. For all x and y in R, if x, y and y x, then x equals y. For all x, y, and z in R, if x, y and y z, then x z. For all x and y in R, x, y or y x. The field operations plus and times on R are compatible with the order. In other words, for all x, y and z in R, if x, y, then x plus z, y plus z. For all x and y in R, if 0x and 0y, then 0x times y. The order is complete in the following sense. Every non-empty subset of R bounded above has a least upper bound. In other words, if A is a non-empty subset of R, and if A has an upper bound, then A has a least upper bound U, such that for every upper bound V of A, UV, the rational numbers Q satisfy the first three axioms, but Q does not satisfy axiom 4. So axiom 4, which requires the order to be Dedekind complete, is crucial. Axiom 4 implies the Archimedean property. Several models for axioms 1 to 4 are given below. Any two models for axioms 1 to 4 are isomorphic, and so up to isomorphism, there is only one complete ordered Archimedean field. When we say that any two models of the above axioms are isomorphic, we mean that for any two models there is a bijection f. Rs preserving both the field operations and the order. Explicitly, f is both injective and surjective. F equals 0s and f equals 1s. For all x and y in R, f equals f plus sf and f equals f times sf. For all x and y in R, x are y if and only if fsf. Explicit constructions of models. We shall not prove that any models of the axioms are isomorphic. Such a proof can be found in any number of modern analysis or set theory textbooks. We will sketch the basic definitions and properties of a number of constructions, however, because each of these is important for both mathematical and historical reasons. The first three, due to Georg Cantor, Charles Méret, Richard Dedekind and Carl Weierstrass, Otto Stoltz, all occurred within a few years of each other. Each has advantages and disadvantages. A major motivation in all three cases was the instruction of mathematics students. Construction from Cauchy sequences. A standard procedure to force all Cauchy sequences in a metric space to converge is adding new points to the metric space in a process called completion. R is defined as the completion of Q with respect to the metric xy. As will be detailed below, let R be the set of Cauchy sequences of rational numbers. That is, sequences x1, x2, x3, of rational numbers such that for every rational epsilon greater than 0, there exists an integer n such that for all natural numbers n greater than n, xm minus xn less than epsilon. Here the vertical bars denote the absolute value. Cauchy sequences and can be added and multiplied as follows. Plus equals times equals. Two Cauchy sequences are called equivalent if and only if the difference between them tends to 0. This defines an equivalence relation that is compatible with the operations defined above, and the set R of all equivalence classes can be shown to satisfy all axioms of the real numbers. We can embed Q into R by identifying the rational number R with the equivalence class of the sequence. Comparison between real numbers is obtained by defining the following comparison between Cauchy sequences. If and only if x is equivalent to y, or there exists an integer n such that x n y n for all n greater than n. By construction, every real number x is represented by a Cauchy sequence of rational numbers. This representation is far from unique. Every rational sequence that converges to x is a representation of x. This reflects the observation that one can often use different sequences to approximate the same real number. The only real number axiom that does not follow easily from the definitions is the completeness of, i.e., the least upper bound property. It can be proved as follows. Let S be a non-empty subset of R and U be an upper bound for ES. Substituting a larger value if necessary, we may assume U is rational. Since S is non-empty, we can choose a rational number L such that L less than S for some S in S. Now define sequences of rationals and as follows. Set U0 equals U and L0 equals L. For each n consider the number Minnesota equals 2 if Minnesota is an upper bound for S set. Un plus 1 equals Minnesota and lane plus 1 equals lane otherwise set. Lane plus 1 equals Minnesota and un plus 1 equals un. This obviously defines two Cauchy sequences of rationals, and so we have real numbers L equals and U equals. It is easy to prove by induction on n that un is an upper bound for S for all n in. Lane is never an upper bound for S for any n, thus U is an upper bound for ES. To see that it is a least upper bound, notice that the limit of is 0, and so L equals U. Now suppose B less than U equals L is a smaller upper bound for ES. Since is monotonic increasing, it is easy to see that B less than lane for some n. But lane is not an upper bound for S and so neither is B. Hence U is a least upper bound for S and is complete. The usual decimal notation can be translated to Cauchy sequences in a natural way. For example, the notation pi equals 3.1415 means that pi is the equivalence class of the Cauchy sequence. The equation 0.999 equals 1 states that the sequences are no-equivalent, i.e., their difference converges to 0. An advantage of constructing R as the completion of Q is that this construction is not specific to one example, it is used for other metric spaces as well. Construction by Dedekind cut. Say Dedekind cut in an ordered field is a partition of it, such that A is non-empty and closed downwards. B is non-empty and closed upwards, and A contains no greatest element. Real numbers can be constructed as Dedekind cuts of rational numbers. For convenience we may take the lower set as the representative of any given Dedekind cut, since completely determines. By doing this we may think intuitively of a real number as being represented by the set of all smaller rational numbers. In more detail, a real number is any subset of the set of rational numbers that fulfills the following conditions: is not empty, is closed downwards. In other words, for all such that, if then, contains no greatest element. In other words, there is no such that for all. We form the set of real numbers as the set of all Dedekind cuts of, and define a total ordering on the real numbers as follows. We embed the rational numbers into the rails by identifying the rational number with the set of all smaller rational numbers. Since the rational numbers are dense, Such a set can have no greatest element and thus fulfills the conditions for being a real number laid out above. Addition, subtraction, where denotes the relative complement of in. Negation is a special case of subtraction. Defining multiplication is less straightforward. If then if either/or is negative, we use the identities to convert them or to positive numbers and then apply the definition above. We define division in a similar manner. If then if either/or is negative, we use the identities to convert to a non-negative number and or to a positive number and then apply the definition above. Supremum. If a non-empty set of real numbers has any upper bound in, then it has a least upper bound in that is equal to. As an example of a Dedekind cut representing an irrational number, we may take the positive square root of 2. This can be defined by the set. It can be seen from the definitions above that is a real number, and that. However, neither claim is immediate. Showing that is real requires showing that for any positive rational with, there is a rational within the choice works. Then but to show equality requires showing that if is any rational number less than 2, then there is positive in with. An advantage of this construction is that each real number corresponds to a unique cut. Stevens' construction. It has been known since Simon Stevan that real numbers can be represented by decimals. We can take the infinite decimal expansion to be the definition of a real number, defining expansions like 0.9999 and 1.0000 to be equivalent, and define the arithmetical operations formally. This is equivalent to the constructions by Cauchy sequences or Dedekind cuts and incorporates an explicit modulus of convergence. Similarly, another radix can be used. Weierstrass attempted to construct the rails but did not entirely succeed. He pointed out that they need only be thought of as complete aggregates of units and unit fractions. A standard approach to show that all models of a complete ordered field are isomorphic is to show that any model is isomorphic to this one because we can systematically build a decimal expansion for each element. Construction using hyperreal numbers is in the hyperreal numbers. One constructs the hyperrationals *q from the rational numbers by means of an ultrafilter. Here a hyperrational is by definition a ratio of two hyperintegers. Consider the ring B of all limited elements in *q. Then B has a unique maximal ideal I, the infinitesimal numbers. The quotient ring B, I gives the field R of real numbers. Note that B is not an internal set in *q. Note that this construction uses a non-principal ultrafilter over the set of natural numbers, the existence of which is guaranteed by the axiom of choice. It turns out that the maximal ideal respects the order on *q. Hence the resulting field is an ordered field. Completeness can be proved in a similar way to the construction from the Cauchy sequences. Construction from surreal numbers. Every ordered field can be embedded in the surreal numbers. The real numbers form a maximal subfield that is Archimedean. This embedding is not unique, though it can be chosen in a canonical way. Construction from Z. A relatively less known construction allows to define real numbers using only the additive group of integers with different versions. The construction has been formally verified by the Untitled project. Schenitzer and Arthon refer to this construction as the eudoxus reals. Let an almost homomorphism be a map such that the set is finite. We say that two almost homomorphisms are almost equal if the set is finite. This defines an equivalence relation on the set of almost homomorphisms. Real numbers are defined as the equivalence classes of this relation. To add real numbers defined this way, we add the almost homomorphisms that represent them. Multiplication of real numbers corresponds to composition of almost homomorphisms. If denotes the real number represented by an almost homomorphism, we say that if is bounded or takes an infinite number of positive values on. This defines the linear order relation on the set of real numbers constructed this way. Other constructions. A number of other constructions have been given. As a reviewer of one noted,